Welcome all to this month's Tunneling in QFT seminar. We're very happy to have Matthew Johnson here, who's at Perimeter Institute and York University, and who has done research in many areas of cosmology, from designing CMB analysis algorithms to understanding the role of string theory in the universe. But for us, he's done lots of work on first order phase transitions and bubble dynamics, and more recently on tunneling, false vacuum decay in analog systems and in real-time simulations, which I think we're going to hear some of today. I also want to highlight that next month we have Anna Kolmu on the 19th of June, who will be talking about some simulations related stuff too. But yeah, please, Matt, take it away.
Yeah, thanks very much for the invitation to come talk to you today. So before I begin, I would just say that I will be describing some of my own work, but I'd also like to take this opportunity to talk about the work of others and try and highlight some interesting things that I think are happening in this area. And to acknowledge the people that have collaborated on the research of my own that I'll present. I have them listed here, and in particular, I want to highlight the contributions of the postdocs and students who I've bolded here, who've done some really amazing work on a lot of these projects that I'll describe. So, what's our goal for today? We're going to try and think about the quantum dynamics of the false vacuum. And so on the left, we have our kind of toy theory, which is going to be a scalar field theory that has a potential with a higher energy metastable local minimum, which we'll call the false vacuum, and then a lower energy true vacuum. And we want to think about ensembles where the universe starts in the false vacuum, and then at zero temperature, classically, nothing would happen. But quantum mechanically, you get the interesting dynamics, we think, that you're seeing in the movie that's playing on the right, which is a simulation of one of the experiments that I'll be talking about in just a little while. So that's our goal for this morning or this afternoon, depending on where you are. So let's talk about the fundamentals of vacuum decay and why this is an interesting and difficult problem. So vacuum decay is a non-perturbative feature of quantum field theories with a nonlinear potential that are not in equilibrium. And so the number of non-words in that sentence should impress on you some measure of the difficulty of this problem, because each of them involve their own complexities. We can't apply perturbation theory. We need to think about complex dynamics, and it's often not possible to do calculations that are simplified by assumptions about equilibrium. And so, but there are well-known approximate techniques that we can use for computing some properties of vacuum decay. For example, the rate of nucleation events and the approximation that they're rare. But our understanding of this process that I've showed you in the movie on the previous slide is neither complete nor totally rigorous. And it's not obvious where different assumptions that are made in these approximate techniques break down. So I'd just like to, most of my slides are going to be a bunch of questions. So maybe we have enough time at the end to talk about some of them, but let me just start flashing some of the questions that I think are relevant and interesting to try and address understanding the quantum dynamics of vacuum decay. So one of them is what are the observables? So, we can compute the rates, but what other things beyond the rates are interesting to compute? In particular, what are things that are actually observable and maybe have phenomenological consequences or would help us understand better the details of the dynamics? There are two different ways to get out of the false vacuum. If you're at finite temperature, you can jump over the top. And if you're at zero temperature, you can go through, and somewhere in between, it's a mix. And so what are the differences of thermal or quantum vacuum transitions or vacuum decay? And what do they look like when they happen in concert together? What is the approximate picture typically that's based on some Euclidean techniques miss? Are there important physics inputs that are just not there? And then, as we go through the talk, I'll just have lots more questions. But a focus that I want to bring is that there is this developing enormous hammer. I have Googled the picture of the world's largest hammer, and this is the world's largest hammer hammering in a nail. And so can quantum simulation be a good hammer to help us solve this problem of understanding the quantum dynamics of vacuum decay? Is another question that I'd really like to try and focus on during this talk. So before we get to that, why don't we just quickly review the semi-classical Euclidean techniques that are typically used to try and understand vacuum decay. So typically what we do is we look for some saddle point approximation to a path integral over field configurations. And the lore, and in some cases you can prove that the dominant quantum contribution at least comes from O4 invariant Euclidean solutions. So these are solutions that only depend on the Euclidean radius in space-time, in four-dimensional Euclidean space-time, where we've analytically continued time. And for the thermal case, those are dominated by spherically symmetric or O3 invariant Euclidean solutions. Okay, and the goal typically is to find solutions with these symmetries that interpolate between the two sides of the barrier. And so sometimes these configurations are called the instanton, the bounce, the bubble. And essentially they look like a field configuration that interpolates in the at 0 Euclidean radius from the true vacuum to the false vacuum at large Euclidean radius. And the importance of quantum versus thermal is determined essentially by how the temperature relates to the mass, because at finite temperature, we compactify the time direction with a periodicity of 1 over the temperature. And if the bubble fits into that cylinder, then typically you're in a regime where quantum effects are most important. But if the bubble doesn't fit into the cylinder, it wraps around, then you're in a regime where the temperature is most important. Okay, so then you take those configurations you've solved for, you put them into the path integral, and you approximate the rate as a prefactor and an exponent, where the prefactor encodes fluctuations around that Euclidean configuration. And then the exponent typically is just evaluating the Euclidean action with that configuration. So that gives you a rate. It gives you a probability per unit for volume, per unit time, per unit spatial volume. And then the story goes that if I want to figure out how this relates to a first order quantum phase transition in the real universe, poof, some critical bubble nucleates. And then once it nucleates from the symmetries of the instanton, we know that the bubble walls expand asymptotically to the speed of light on hyperbolic trajectories, and that inside the light cone emanating from the nucleation center, you have an open FRW universe. And for the thermal case, again, poof, you analytically continue the thermal instanton, and that's a static configuration. And then you have some probability that that static configuration, which is in unstable equilibrium between collapse and expansion, some of the times will expand, and some of the times it collapses. And then the other piece of the lore is that nucleation is this kind of Markovian stochastic process. And so these bubbles nucleate at random times and locations and subsequently expand. And if you're in a universe that is not accelerating, then the phase transition from the false vacuum to the true vacuum will eventually complete. And if you live in an expanding universe, then sometimes it does and sometimes it doesn't. And that's an interesting problem that I won't touch on at all today. Okay, so that's a lightning overview of kind of the standard picture. And this is an extremely useful computational tool, but it comes with a set of questions that I think anyone who's thought deeply about this problem has. And so one of these questions is the aftermath. So how literally do we interpret this analytic continuation that tells us what happens when the bubble forms, the poof, if you will? And in particular, you might ask, well, is this some instantaneous transition if I'm watching this occur, or is there some precursor that happens before the bubble nucleates? When is the configuration classical enough to even talk about the bubble forming at a specific time? So is this picture totally naive to think that there's some classical field configuration at the time of nucleation? How is the symmetry of the instanton related to each individual nucleation event? We're computing some kind of expectation value, and so you might expect that the fluctuations around it could be important and change each individual realization looks like. It might be different than the average. And related to that, just sort of what kinds of fluctuations would a typical realization have around that mean? What are their properties? We know something about that from the prefactor, but in detail for the time evolution, what does that mean? What does that look like? Another thing that you probably ask yourself is, how do we investigate multi-bubble spacetimes? We have these Euclidean solutions that tell us about individual bubbles, and we have a set of approximations that allow us to compute a rate when the bubbles are dilute, in other words, when the nucleation events are rare. But you might ask yourself if the individual nucleation events could be correlated. If I form a bubble somewhere, is there a higher or a lower probability of forming another bubble nearby? What happens in the limit where the rates are fast and you can't make this dilute instanton approximation? In detail, how does percolation proceed? Is it really this totally stochastic Markovian process where things percolate essentially at the same time everywhere up to Poisson noise fluctuations, or is it something else? And what about the failed nucleation events, the subcritical bubbles? Are those something that you can meaningfully think about? And finally, another question you might ask yourself is, well, this Euclidean computation is done in some sort of H-bar expansion. And so which quantum effects are important? And there are multiple ways that a quantum field theory can be quantum. So there are fluctuations, like vacuum fluctuations in the field and its conjugate momentum that obey the uncertainty principle, essentially, mode by mode. Is that the relevant, important quantum effect that's driving the vacuum decay? Are virtual particles the important driving effect? In other words, sort of off-shell field configurations that don't conserve momentum? Or do we have to worry about renormalization? So an interesting question that maybe I could explain the answer to, but I'm still honestly a bit confused on this point, is when I'm evaluating the instanton, the bounce, the bubble, should I be putting in a profile for the bare Lagrangian or the Lagrangian with renormalized parameters? And where should I put that? Should I put that in the bounce, the bubble configuration that goes in the exponent, or is that something that's supposed to go in the prefactor? And I think that's a subtle and interesting question that kind of depends on how big these effects are and your choice of assumptions. So there are these questions, right? And I think I certainly would like to know the answer to some of these questions, and there are things that I don't really know necessarily how to address in the Euclidean picture. So enter quantum simulation. What if I had an experiment that I could poke and probe and change the parameters of to simulate vacuum decay in the hopes of answering some of these questions? In other words, to do the computation without approximation, and to do the computation in a way that I really get to study the real-time dynamics. And so, essentially what we're talking about when we say we want to simulate vacuum decay with a quantum simulator We want a quantum many-body system made of stuff that I can build or arrange in a laboratory that exhibits some kind of metastability. And so on the most like basic level, you could go upstairs and make a pot of coffee, or you could get a really clean bottle of water and put it in your freezer and then shake it. And there are every day in our life examples of nucleation or metastability, and then first order phase transitions in solids and liquids. And that's one way of getting at it. It's not quantum, but the physics is everywhere. And I don't know, just in preparing for this talk, I was Googling and I found a really nice review from 2002 that talks all about nucleation theory in solid and liquids, and you can learn why champagne bubbles form on the side of your glass and not in the bottle, and how that's really important. It's fun. But if you want to go quantum, there's lots of activity in trying to build and design real experiments that try and get at this. And so this is a non-exhaustive list, but let me kind of categorize the existing efforts to quantum simulate vacuum decay into 3 boxes. One box is to create spin chains, which can exhibit forms of metastability, and the hardware that you can use to implement spin chain Hamiltonians. You could use a quantum annealer like a D-wave quantum computer. You could build lattices of optically trapped ions where the interactions are tuned such that you get some model that looks like a spin chain. And I'll have a few slides in a second to discuss some of these proposals in a little bit more detail. You could design lattice gauge theories that exhibit metastability and are implemented on different types of quantum hardware. So again, there have been efforts to find lattice gauge theories, in particular 1+1 dimensional QED with a constant electric field where you can have Schwinger pair production. That's kind of like vacuum decay. You can implement that on trapped ions, quantum hardware. You could implement it on universal or digital quantum computers like superconducting qubit machines, IBM, and so on and so forth. Or you could look at hybrid quantum classical computing methods also, as well. That's been done to investigate this process of vacuum decay. Or you could look at systems where you have Bose-Einstein condensate that possesses excitations which can be metastable. And then you could study the evolution of those excitations as they transition out of metastability. And most of the current efforts in this direction involve mixtures of more than one species of atomic state that you set up in a special state, and then you study its evolution. Most of the talk, I'm going to focus on this last thing because that's the thing that I have a personal stake in and have worked on. But before we talk about that, I just want to really quickly overview what is done in these other approaches. And just for your reference, you can go back later and read some of these papers. It's really interesting stuff happening. So most of the efforts that try and simulate false vacuum decay using spin chains employ this mixed transverse field Ising model here. So you have a Hamiltonian describing a set of spins, which neighbor by neighbor, or they could have longer range interactions, are coupled, and then have magnetic field applied that is different in the Z and the X direction. And in this case, the free energy as a function of the magnetization can have a metastable state where the false vacuum corresponds to the chain being all spin up, the true vacuum corresponds to the chain being all spin down, and a bubble or a domain wall in between them corresponds to some set n of spins that are down in a sea of up spins. Okay? And you can get propagating excitations You can get wall or kink, and I guess you could think of this also as kind of a kink anti-kink pair that can form in the spin chain. And there are lots of different proposals. Some of the references I've listed on the previous slide, but there are other references that's just a representative set that try and implement spin Hamiltonian like this on different kinds of systems. Okay, and so here is just two pictures from papers that implement this, one on a quantum annealer, a D-wave machine, and the other on a trapped ion lattice. And so in both cases, on the left, this is an image that shows as a function of the strength of the transverse field, what the bubble configurations look like that are observed. And so you can get bubbles that are nucleated that are many, many spins. So this is 306 spins big. That's the size of the critical bubble, down to much smaller, kind of almost individual spin bubbles. And this has been observed in real evolutions of a D-wave machine, and there's some comparison to theory that, again, is sort of qualitatively reasonable. And then on the right, here's a picture of some bubble formation, or these spontaneous formation of these spin domains in a trapped ion machine where there's something like order 10 spins, right, that are evolved in time, coupled with this Hamiltonian. And as a function of something that determines the strength as you go left to right, well, that determines the barrier as you go left to right. On the left, nothing happens, bubbles don't form. And then as you go to the right, the rate gets faster and faster. And then on the bottom, there's some indication that the domains that you form are growing. And so these bubbles form and then they grow in the spin chain. And again, there's, because it's Hamiltonian, that for a small number of degrees of freedom, you can just you can make analytic comparisons between these experimental results and what you expect from theory. So the other thing you can do is try and implement a lattice gauge theory that exhibits metastability onto different kinds of hardware. So here, a canonical example is to construct some Bose-Hubbard model. So that's a set of sites, and then you have a Hamiltonian that describes hopping between sites. That's this kinetic term, the first thing with the J out front. And then you have some potential that you've engineered by applying different kinds of external fields. And in this case, you can map this Bose-Hubbard model to 1+1 dimensional quantum electrodynamics, where the last term is what you get if you had a constant electric field. And so if you have a constant electric field, then there's some probability you form electron-positron pairs. Here, the meaning of electron-positron are different spin configurations, like in the previous slide, or different configurations of how many atoms you have at each site, 1 or 2. And then those can evolve and neutralize the background electric field. And then you build up a density of particles of these electron-positron pairs, or these propagating changes in the occupation number at each site. And so, back in 2016 on a 4-qubit trapped ion quantum computer, the Schwinger pair production process was observed for the first time, until recently. There's this paper from last year where now the number of qubits, if you will, is order 10 or a little bit more. And you can really in detail observe the increase in density of particles and study this process in a more quantitative manner. And so these are real tools now that you can use in the lab to explore pair production in 1+1 dimensional QED. You can also do this for non-abelian gauge theories. This was a fun paper that my colleague at York University, Randy Lewis, and his student Ellie Kavaki did, where they looked at SU2 in a 3-dimensional box, which has one of the box boundary conditions twisted so that it's not the Pac-Man universe that's totally periodic, but it's some rotated Pac-Man universe. And here you can have configurations of the gauge fields that are metastable, and then they can decay. In this case, the thing they decay into are these objects or field configurations called toralons. And then they you know, with 12 qubits can start to think about the quantum dynamics of these non-abelian gauge theories and their metastability. So that's just kind of a flavor of some of the efforts in this domain. And so, you know, let me talk a little bit about the opportunities here. So in each of these examples, you can study real-time quantum evolution. So that means that you could measure things like the decay rate empirically. You could think about the bubble dynamics. So what do they look like when they form? How do they evolve after they form? People have observed real quantum effects. So for example, in the Schwinger pair production example, there have been measurements of various types of quantum entanglement associated with the production of pairs from the vacuum that induce measurable long-term quantum correlations in the chains. The effect of having multiple bubbles and the effect of bubble interactions on the dynamics has been studied, and that actually does have important implications for the dynamics of these different chain models. And people have observed sort of non-ergodic or non-equilibrium phenomenon in the literature on many-body quantum mechanics. These are called scars, but they have been associated with sort of the failed nucleation events or subcritical bubbles, which I think are connected to field configurations called oscillons, and I'll talk a little bit about that later in my talk. But there are limitations for these systems. So the variables that are involved are intrinsically discrete. So, you know, they're built from spins, so up and down. There are not many degrees of freedom. And so talking about a continuous quantity like the magnetization, that's in fact quite discrete, right? And so these are not, you know, real scalar field degrees of freedom that are some real number, right? They're discrete degrees of freedom. They're noisy typically, so to do anything in this regard, you need many shots, you need error mitigation techniques, and it's challenging to do time evolution on current noisy quantum hardware. And typically they're not relativistic, meaning the dispersion relation of the propagating degrees of freedom is not a relativistic dispersion relation. It's a non-relativistic dispersion relation. And so that might obscure connections to some of the questions that we would be interested in talking about a relativistic quantum field theory. So that's some of what exists. But maybe now let me step back and say what, you know, like what do we want, having described some of these efforts from an experiment? And I think the goal would be to have sort of fully controllable and interpretable experiments of vacuum decay, meaning low temperature quantum driven, in a relativistic quantum field theory. And so some of these efforts tick a few of the boxes for these goals, but none of the things that I just described tick all of the boxes. And so let's like dig in maybe a little bit for the wish list, which you could contrast with the limitations that I just presented. So, you know, we want many degrees of freedom. We want continuous variables. We want something that's intrinsically quantum, something that's relativistic. We want a setup where we could do detailed forward modeling so that when we measure things from the experiment, we have some theoretical construction to which we can compare them and meaningfully learn about the underlying theory. And we want a set of observables. So we want to know if we do the experiment, what is it that we are going to observe that's going to try and answer some of the open questions that I've raised earlier in the talk. And this may be possible with BEC analogs, which is the thing that I'll now turn my focus to and describe for much of the rest of the talk. So there is a group of us. If you do not know about the quantum simulators for fundamental physics consortium, this is a set of theorists and experimentalists, mainly in the UK and Canada, that are trying to develop ideas in this direction. So quantum simulators of fundamental physics in cosmology, that would be this, how do we understand cosmological first order phase transitions question, but also for black hole analog systems. There's a really amazing team. Here are some of the members of this team. And then some time ago, it's a bit dated, 2023, there was a New Scientist article about some of the efforts that were being made. And so the team, when it comes to thinking about this problem of false vacuum decay, both from a theoretical perspective, but also building laboratory experiments, I've listed here. So in the UK, there are people at Newcastle, there are people in Nottingham, there are people at Cambridge, and people at Durham. And then in Canada, there are a set of researchers, mainly at the Perimeter Institute for Theoretical Physics, that are thinking about these questions. And on the experimental side, there's the group of Zoran Hadzibavich, who is in Cambridge, that is working on experiments that can realize this idea of false vacuum decay. So how does it work? So you, at the level of theory, can describe a two-species BEC. So you could think about that as a cloud of cold atoms that contains two different atomic species. And their mean field evolution can be described by the Gross-Pitaevsky equations, which I've written here. So these look kind of like the Schrodinger equation if you ignore the terms in the middle, which are nonlinear. And so this is a kind of a nonlinear implementation of the Schrodinger equation. And the two relevant terms beyond the usual time evolution and gradient term would be things that have to do with scattering. So you can have self-interactions, and these are just like point-like, point-like interactions, 2 to 2, between a species and itself, or it can be between the species 1 and species 2. You can also have an induced mixing or coupling term that you can introduce by irradiating the system with external electromagnetic radiation. And you can, to some extent, tune the scattering lengths here, or the scattering strengths, by essentially defining what these two species are. Typically, these two species are two hyperfine states of some convenient atom that's easy to cool. Most of the experimental stuff I'll talk about involve potassium, but it could be different atomic species that your laboratory setup is set up to efficiently cool and study. And then you basically can define the properties of these two states by applying a magnetic field and splitting the state at your will. Okay, and then in doing so, you can, to some extent, tune these scattering lengths. So if you look at this set of two nonlinear Schrodinger's equations, you change your basis to an amplitude and a phase. Then it turns out you can, in the case of a homogeneous condensate, so I haven't put anything about the trapping here, there's no trapping potential in these equations, integrate out the density and the total phase, they're just Gaussian variables, and end up with a equation or Lagrangian for the relative phase that looks like a scalar field that has a relativistic dispersion relation and a cosine potential. And if you want to see some details, one place you can find it, although you can find it in many places, would be the reference down here. And so if you were to go back to the Gross-Pitaevsky equations and do perturbation theory around small fluctuations in the relative phase of the two wave functions, you can just compute in the full theory what the dispersion relation looks like. So the frequency is a function of wave number. And what you find is that in the IR, so at low wave number, you get this advertised relativistic dispersion relation, which has to do with the sound speed of the relative phase mode. And then in the UV, you just recover the dispersion relation you'd get from the Schrodinger equation. So something that's quadratic in K. And then, so at low K, in the IR, you have a theory for the relative phase that just looks like a relativistic scalar, a Klein-Gordon field. And in the UV, you have something that has a quadratic dispersion relation. And the UV scale that's relevant to this problem is something called the healing length, which essentially tells you if I put a density depression in the condensate, on what length scale does it return to the mean density? And you can only make depressions of a minimum size, and that's this healing length. So you have this crossover where the UV completion of our relativistic scalar field with a cosine potential is the condensate itself. Now, to make a false vacuum from that cosine potential, you can remember, one way to do it is you can remember from your undergraduate physics that, the equation of motion of a pendulum has a cosine in it. And if I shook the base of the pendulum, then I can make a pendulum that has a metastable state where it oscillates straight up instead of down. And the equivalent of that is to take the mixing term, which is induced by this external RF that we can control, and you just shake the amplitude, right? And in doing so, if we go to our effective relativistic scalar theory, then you obtain a potential that looks something like this, where you can tune the depth of the false vacuum, which lies at the maximum of the cosine, at your will by changing the strength or the amplitude of this modulation that you've introduced. And so that's going to be our theory in this analog. And then you can study the properties of that false vacuum. That's something, one of the most recent examples. I have a paper that I've cited here. For example, you can ask the question, at low temperatures, if I'm in the ground state of the condensate around this metastable configuration, does that map on to the vacuum state of the Klein-Gordon theory? And so happily, the answer is yes. So not only do we think we get a potential that has a metastable state, but that if we think about the fluctuations in the full UV complete theory around that metastable state, they really look like the vacuum fluctuations of a scalar field around the false vacuum. And then the other thing you can do is you can think about generalizing to any possible coupling, studying in which cases the different degrees of freedom decouple, and asking, do you always get something that has a relativistic analog? And happily, again, the answer is that there's some reasonable range of kind of realistic, accessible experimental parameters where you get this IR theory that looks like a scalar, or that looks like a relativistic scalar, and has a metastable false vacuum. And so I've cited a paper here that was led by Alex Jenkins that describes some of those efforts. Okay, so that's the theory, and this is the experiment. There is a BEC in a laboratory somewhere at Cambridge University that is now able to trap BECs. So don't ask me about any of the details of these pictures. It's just the left is a cool picture that some of the theory people got to go visit the experiment. The right is an image of the apparatus that I could not describe to you at all. But on the bottom left, you see proof that that you can trap the condensate in very unique geometries. And then on the bottom right, we see that the experiment has the ability to image this relative phase. Okay, so if you set up on the bottom right figure in some initial configuration in a uniform relative phase, then it can drop and oscillate and create interesting field configurations that are on the right. And so you can time evolve and image the relative phase. So, you know, hopefully in the coming few months, the apparatus will evolve to a state where we can start to really dynamically evolve condensate that is put in this false vacuum state, and then hopefully eventually get to a regime where you're really doing quantum mechanics. Now, on the theory side, one of the big efforts is trying to forward model this experiment, because if you remember, one of the goals to try and answer some of the open questions was to have a setup that you could really rigorously forward model. And so a typical set of approximations that are employed to study theoretically these cold atom systems. In the low temperature limit, people employ something called the truncated Wigner approximation, which is essentially to populate the initial state with modes that are drawn from the ground state, which like happily is a Gaussian. And so that the Wigner functional has the interpretation of a real probability functional, and you can draw configurations from it in a way that is sensible. You can also apply this to scalar field theories. This is an example where we tried to address this for the question of quantum tunneling, but this is also essentially what people do when they do preheating simulations in the cosmological setting. And then at high temperature, you can add a stochastic noise term to these fluctuations, and that is something that is being led in the QSIM-FP by the group at Newcastle. And I just want to advertise another paper by some of the people here at PI, led by Andrei Shkarin and Sergei Sibiryakov, where they have some new results on how to effectively implement stochastic field theory simulations. And this could be relevant to anyone who does anything like this. It's a cool paper, you should read it. Okay, so here is an example. Credit to Alex Jenkins. Sorry, I forgot to put that on this slide. That compares the BEC with the full evolution of the Gross-Pitaevsky equation in this truncated Wigner approximation to what you would get if you had just the scalar field theory analog. And you initialize these two simulations with the same exact initial conditions. So this is the mapping of the fluctuations around the ground state to the vacuum fluctuations. And you can see that, you know, matching those initial conditions, at least for this first bubble that forms, it happens at essentially the same time and the rate is the same. But then there are differences. So on the left-hand side in the full BEC, you see many bubbles form, whereas on the right, there was only a single bubble. And so there could be interesting things here in comparing the rates and how we should think about that. But I mean, you can think visually, the goal of this effort is to really use the thing we measure on the left to learn about the theory on the right. And so we really would like to get to a stage where these two things can match. Sorry. In doing so, there are like interesting hiccups and things that happen. So again, to advertise a paper that was written led by Alex Jenkins that I wasn't involved in, you know, you realize that if you just trap the condensate with a steep wall, the cost in action of creating half a bubble is exponentially less than the cost in action of creating a whole bubble. And so essentially the rate to form bubbles around the boundary is way faster. It's exponentially faster. And so if you didn't cleverly engineer the trap that you're going to put these atoms in, then essentially everything just comes from the boundaries. And then the solution to that is to put a density trench around the outside, and that's on the right. And there you see that on the time scale of this simulation, you never get any bubbles on the boundary. In fact, they all just come from homogeneously from the center. And so there are these interesting questions and opportunities for trying to do this rigorous comparison between experiment and theory that I think are pretty interesting. And then there are some open questions that we don't really know how to address yet. So for example, you're taking the system and you're shaking it, and that can induce parametric resonances. And we expect those resonances to be damped if they're pushed into the UV outside of the regime of validity of this IR relativistic scalar field theory. But then the question is, how are they damped? And are they damped on, are they sufficiently damped that we don't end up with situations like on the right in this image where the evolution is just driven by parametric resonance and not bubble formation? Another interesting question is normalization effects. So, you could derive from the Gross-Pitaevsky equation some effective Lagrangian, but that is not necessarily those are not necessarily the interactions that the fluctuations in the experiment are going to see, because you have interactions between UV and IR modes that drive normalization effects and change the effective parameters that the experiment sees. And so if you really want to do a quantitative comparison between the experiment and theory, you need to figure that out. Otherwise, you're going to be making predictions that are not necessarily compatible. And so then you could think about interesting measurements you might be able to do in the experiment to sort of determine those parameters that you could then put into your model. But I think this is a really interesting set of questions that are still outstanding. However, there are already first results on two-component BECs and getting observing vacuum decay. So in this recent paper, thermal vacuum decay was observed in a one-dimensional two-component BEC. Here's the image of a bunch of runs that are stacked of the experiment, and you can see that the blue is the false vacuum and the red is a little true vacuum domain that forms and then expands. Here, the relevant degree of freedom is the relative density of the two components and not the relative phase, basically the magnetization. And it's, checks some of the boxes, but not all of the boxes of where we want to go. So it's thermal, it's not relativistic, the condensate is inhomogeneous, so it would be like having bubble nucleation in some curved geometry. And so there is still a lot of effort to be made to get to the quantum regime to get a fully relativistic analog, but this is a really interesting first result. Okay, so I'm almost out of time. So let me just briefly talk about the question of what would we want to observe. So given an ensemble of nucleation events, I do some experiment, how would we characterize them? One thing you could do is you could measure the decay rate. And, in Euclidean theory, that's all we get. But in fact, it's only correct in some situations. And it misses kind of the rich quantum dynamics. So what can we think of that's beyond the decay rate as something interesting to observe? And something that I've explored with collaborators and also some other people at Perimeter Institute have been exploring is using stochastic field theory simulations in 1+1 dimensions to think about the different types of things beyond the decay rate that you might observe. So one of the things could be the bubble-bubble correlation function. So if I nucleate a bubble here, is it more probable to form a bubble nearby? Studying precursors to bubble nucleation. studying the critical bubble, so like literally measuring the average bubble configuration at nucleation appropriately defined. And then also realizing that bubbles never form at rest, but instead have a distribution of velocities. And that's another possibly interesting observable. I think you can rigorously answer all of these questions at finite temperature, and then generalizing them to zero temperature is something that we've done, but I would say is not totally rigorous, and that's kind of an open question and an interesting target for all of these experiments once we have established that these are interesting things to go after. So I'm briefly just going to go through these and highlight a few results. So advertising work that I wasn't involved in, but was done here at Perimeter Institute, a set of thermal stochastic 1+1 dimensional sims was done where you could contrast the rate when I couple to a bath. So when I add a noise term to this stochastic differential equations, with the case where I have the system in thermal contact, and then I remove the bath. So then basically the thermal effects are all in the initial conditions. And here what you see is that the Euclidean computation doesn't agree with either of these things. And so that says that even when you're coupled to the bath, there are interesting non-equilibrium effects that are important. And when you decouple from the bath, your decay rate now is time dependent. And that leads to something that these authors called the classical Zeno effect, which is that if you are in an unlucky realization that has lots of IR power to make bubbles, you decay right away. But if you're in a lucky simulation where you have not lots of IR power to make bubbles, you live for a really long time. And so that means that on a realization by realization level, you will have a different decay rate. And the things that live long will live even longer. So if you survive to 85 and you do not have any health problems, you're probably going to live to 100. But if you're 45 and you're already in the hospital, then you probably won't. Okay, so this is just some of those points. There's a large difference between a kind of a closed system where it's just initial conditions and one coupled to a bath. For a single scalar, at least, you can't maintain thermal equilibrium, and that's why you don't agree with the Euclidean rates. And there's lots of interesting stuff here, and the dynamics is crucial. At zero temperature, who knows? Okay, the other thing you can do is you can try and answer this question: is it more probable to find a bubble nearby? And that's something that in a student led by my student Dalila was done. And the answer is yes. You can measure the correlation function, and you see that there is a correlation sort of at a few bubble radii. So if you form a bubble, you're probably very likely to form another one nearby. And if you form a bubble nearby, you are of one phase, then you might be less likely to form a bubble of an opposite phase. And then the interesting thing here is that just like we measure the galaxy-galaxy correlation function in cosmology, we learn about the distribution of dark matter. Here you can measure the bubble-bubble correlation function and learn about the vacuum fluctuations or the thermal fluctuations. That's encoded in the shape. Bubbles never form at rest. So if you look at individual realizations of these stochastic simulations, you see that, as on the left, most of the bubbles form with some non-zero center of mass velocity. And then you could boost them into their rest frame and measure the distribution. And you find that that is essentially, in the thermal case, well fit by Maxwell-Boltzmann. So the width of the distribution is just proportional to the temperature. The bubbles are like real particles. They're getting kicked around in the bath. And you can measure their velocity in that way. And it agrees with that theoretical picture. You can stack the bubbles. So here is the stack of many bubbles measured at rest. You can find their ensemble average, and that matches with the critical, the prediction for the thermal critical bubble. So that's kind of a validation that that picture is capturing something right. You could check explicitly that that's true. So if you take a slice a bit after the quote time of nucleation and evolve it, you get an expanding bubble. But if you take a slice just before, you get a bubble that is subcritical and then collapses. So in the thermal case, remember, the instanton is supposed to be something that's in unstable equilibrium between expansion and collapse, and you can check that that is actually what happens. You can address the question of what happens before a bubble nucleates. I'll skip that, but it is essentially a field configuration that is called an oscillon. In fact, that's where oscillons came from, thinking about subcritical bubbles. And if you look at the sims, you see that in advance of bubble nucleation, at least in many cases, I don't think this is universal, but it's true in many cases, you have this very long-lived precursor state where you have a localized field that is a lump of field that is oscillating, and that is the thing that ends up catalyzing the nucleation of the bubble. Okay, now I'm basically done, but I want to leave you with a thought. That's a fun thought experiment. So given that there are these classical precursors, and in some of the quantum simulation stuff, people have observed these quantum scars, which I think are essentially the quantum mechanical version of these oscillon precursors. Could you build a universe decay detector? And if you can, let's patent it. And then we can become the supervillains of the universe and be like, we'll tell you when the vacuum's going to decay. And then we can have the machine that prevents the vacuum from decaying by like sending in a bunch of interfering modes, and then ask for $1 billion and then fund our future efforts of understanding tunneling in quantum field theory. Okay, so I think I'll leave it at that because I'm at the time, and thanks so much. Yeah.
Thank you very much for a very nice talk. Great overview. Yeah, if anyone has, I know you have to go shortly after this, but do you have time for a couple of questions? If anyone has any questions, please put your hand up in there.
I can stick around. Yeah, no problem.
Please put up your hands. But while we wait, I'll just ask a quick one, which is we have someone already. I'll go second. So Yash, if you'd like to unmute yourself.
Yeah, hi, I'm Yash Parekh. I had one very silly question, if you may. So let's say we have some quantum field theory, some field theory basically, some scalar fields, and then we will have a metastable state and a true vacuum. So quantum mechanically, a bubble will form, and then we will go from the metastable state to the true vacuum. And as you said, if we are in a thermal, and then if we give some temperature, we will automatically come to the true vacuum. But what if we say we start with a zero temperature quantum field theory and we raise the temperature? Then what will happen, if you can shed some light on it?
So I think the time scale matters. So clearly, if you raise it so slowly that the vacuum decays before you care about the finite temperature, then it's just the quantum decay as usual. If you do it really fast, then it depends on what temperature you raise it to. So then you could be in a regime where the thermal effects are most important, and then you don't care about quantum mechanics. But I think the intermediate phase is probably the most interesting, where you ramp things up slowly enough that you care about the mixture of the quantum and thermal effects. And in that case, I don't think we really know what the answer is. But that would be an excellent proposal for an experiment that you could do if you had a quantum simulator of vacuum decay, is you could, study that process.
Yeah, thank you. Thank you.
No other questions?
Maybe I can ask one thing.
Definitely.
Yeah, when you were discussing these precursors and oscillons, is the frequency of the oscillon dependent on some property of your setup, or is this happening spontaneously? Can you control it? That's maybe one question. And the other one is, can you tune it to kind of catalyze, to have some resonant effect in the decay rate?
Mm-hmm. Yeah, so the first question is, what is the frequency? So we don't inject them, they form dynamically.
Right.
And here is a spectrograph of the, basically if you take trajectories that follow the oscillons, that's the black lines in the left panel here. You basically just trace the maximum of oscillating field configurations. And you ask about their frequencies. You get a histogram that is on the left, okay, the blue one. And so you get things that have a variety of frequencies, but they're peaked at some value, right? So there's kind of a most typical one. And then in the orange, you have what you'd get if you just like put random lines and you measured what the frequency of oscillations on those random lines is. And so, yeah, the important take-home point there is that the frequency of the oscillons is always less than m, right? Which means
Below
it's
the mass, okay.
like a bound state. Right?
And
And then on the right is like the power spectrum, right? And so there you see, the power is peaked around some configuration that is the, looks like the oscillon. And yeah, so I mean, the properties of the oscillons depend on the potential, roughly. Your second question was, can you engineer situations where you could use a cloud of oscillons to kind of catalyze decay?
yeah.
Yeah, so there's an interesting paper from way back, like around the time of when oscillons were thought of, that talks about exactly that. So it's a Glaser paper from like 97, I think, where they basically have some quench-like thing where they start not at the false vacuum, but like a little bit above it. And then you have an oscillating configuration in a potential that really likes to make oscillons. And so you essentially make a cloud of oscillons, and then that catalyzes decay way faster than the rate you'd have if you had started with a field configuration that was exactly at the false vacuum. And so for sure, these oscillons have some role in catalyzing decay. An interesting question that I think, that is, we know the answer to, is that when you compute the thermal rate, does that include that effect? And I think the answer is yes, because in these sims, you can measure the thermal rate, and then you could, well, okay. The answer is maybe. That you can like compare the empirical measurement of the rate to the theoretical rate. And there are some cases where the agreement is better than the one I showed you on the other slide. And in that case, maybe that calculation is incorporating this effect already, the Euclidean calculation. But I think that's an interesting thing to think about and flesh out. Yeah.
Thank you.
Any more questions from the audience? Yeah, we have one more. Fun?
Hello, can you hear me?
Mhm.
Okay, so I just wanted to ask you about this truncated Wigner approximation. Could you maybe comment a little bit more on that? Is this like for numerical simulations, or is this?
Yep, that's for numerical simulations, exactly.
I think it might be related to some ergodic hypothesis or something.
Well, it's essentially that you want to draw initial conditions for the simulation that are consistent with measurements of the vacuum state. And so if you like, you have the uncertainty principle part of quantum mechanics. So you have something that scales like h bar, which is the amplitude of those configurations that you've drawn. And the reason that that's kind of possible is that for, at least for a massive scalar with no interactions, every mode of the field is just the vacuum modes of the field are all just Gaussian, right? And so if I have a bunch of wave functions for each mode of the field that are Gaussian, I can build a Gaussian wave functional, and then I can meaningfully draw configurations from that Gaussian thing. And then I evolve it in time with the classical Hamiltonian, which could include all of the nonlinear interactions. And so, but it only has nonlinear interactions at the level of classical physics. So you can't do things like go off shell, or you can't have virtual, you don't have virtual particles. You don't have loops in the interactions, not quantum mechanical loops. And so you capture sort of the uncertainty principle part of quantum field theory, but not the other ways that a quantum field theory is quantum. And that's kind of the best you can do with a classical computer, unless you were able to understand how to encode those other effects, like going off shell, into some kind of stochastic noise term. And that's something that people have talked about and maybe is possible. And then you could do something like the second thing on this list, which is instead of coupling to a thermal bath, you could couple to like a quantum bath, which is kicking your field in ways that are consistent with going off shell or making virtual particles. But that's something that I don't think has been effectively implemented. Maybe that's a bit of an overview, but if you had a more specific question about some of the details, I'd be happy to answer it.
Yeah, because I've always read about these Wigner functions in terms of loop expansions or gradient expansions. So I was wondering if it was like some sort of expansion in H bar or something like that. But it seems to be maybe a little bit different, right?
No, it is an expansion in H bar. And so if you like, another way to think about this would be Ehrenfest theorem. So if you go to the quantum mechanics case, you're looking at the time evolution of expectation values. And so if I had a potential that was like constant, linear, quadratic, you can get that to leading order in H bar, but then like the next order in H bar would tell you about like a cubic part in the Taylor expansion of the potential. And so if you like, this is the H bar expansion we're doing here. And we don't know how to go to that cubic one, because in the field theory version, then you'd need to understand this kind of like, what does it mean to add this quantum stochastic noise into the equations of motion? But at the quadratic level, if you remember the harmonic oscillator, like the time evolution of the expectation value is just the classical trajectories. So it's the same kind of thing that's happening here. And so you can think of the H bar expansion that we're doing in truncated Wigner as kind of like the field theory version of Ehrenfest theorem.
Okay, thank you.
I think we're a bit over time, so maybe let's leave it there. But thank you very much again, Matt, for that really nice talk. And
Thanks for
see people in a month if they want to join for the next one, which will be Anna Kormu.